Welcome to the Mechanics of Solids lecture series. In this series of videos, we're working problems of beams with axial loads. The objectives are to compute the normal stresses in a beam considering a combination of axial force and bending moment. Here's an example that comes from the Mech movies by Timothy Philpott with the website as indicated. The problem statement reads, pipe AB, which has an outside diameter of 125 millimeters, wall thickness of 8 millimeters, supports a uniformly distributed load of 10 kilonewtons per meter. We're asked to determine the reaction forces at A, the axial force in member 1, and the normal stresses at points H and K, located 0.9 meters above pin A. Okay, and we're given the picture there. So we're given pipe AB with an outer diameter of 125 millimeters, an inner diameter of 125 minus 2 times the thickness is going to be 109 millimeters, and we're basically given the sketch, which I will summarize with a free body diagram. We're asked to find the reactions AX, AY at the support, the force F1, all in kilonewtons, and we're asked to find the stresses sigma H and sigma K at points H and K, and we should find those in units of megapascals. I chose this problem because it's a nice comprehensive problem that combines a lot of what we've done already into a single problem. We have to recall our knowledge of statics and do some good static analysis for this problem. We have to draw a bending moment diagram for the beam, calculate both axial force and bending moment at a specific point, and then evaluate the stresses. So we'll start by drawing a free body diagram of the pipe, which I'm going to do over here. There's the pipe section itself. First thing I'll put back on is the load, the distributed load. Even though it's a column, the distributed load acts in very much the same way, so don't let it confuse you. Distributed load of 10 kilonewtons per meter. Then we have the reactions at A, which I'll label A sub X and A sub Y. And we have the force F1, which is pulling down, tension in the cable. I'm going to decompose this into components F1X and component F1Y in the X and the Y direction. And finally, I want to denote that my overall length is 2.5 meters. Okay, so starting out with some basic statics. Often I start with a moment equation, but this time recognizing the symmetry in the system, I'm going to start with sum of the forces in the x direction equal to 0. So I have F1x plus AX minus the total load, total force due to the distributed load, 10 kilonewton per meters times 2.5 meters gives me 10 times 25 kilonewtons. Set that equal to 0. Now recognizing the symmetry of the system, the reactions are going to be equal. So I can say F1x equals AX equals 25 kilonewtons divided by 2, or 12.5 kilonewtons. Next I'll sum forces in Y. Sum forces in Y equal to 0 tells us that A sub Y minus F1y is equal to 0, or A sub y is equal to F1y, but I can't solve for either of them until I gather some more information. So for now, I recognize that A sub y is equal to F1y. Okay, finally, I need to dissect or analyze the relationship between F1x and F1y based on its geometry. So let me draw the diagonal F1. There's not enough free body information in my free body diagram to determine this, but going back to the original picture, the length of the cable for the force F1 is 2.5 meters in the y direction and 1.5 in the x direction. So that'll give us a diagonal length, which is the square root of 1.5 squared plus 2.5 squared, which is 2.92. Okay? So my x component, f1x, is equal to 1.5 over 2.92 times f1, and f1y is equal to 2.5 over 2.92 times f1. Okay, f1x we know, we already solved for, it's 12.5 kilonewtons. We manipulate this equation to evaluate f1, which we would find is equal to, excuse me there. Which we would find is equal to 24.33 kilonewtons. And from the second equation, then we can solve directly for f1y, which we would find is equal to 20.83 kilonewtons. And that also gives us our value for a sub y and the total compression normal force passing through the pipe of 20.83 kilonewtons. Okay, I'm going to stop here and continue this example in the next video.